Carl Sagan once shared a thought that still echoes through the ages, a reminder that calls out to the curious in all of us. He said, "Somewhere, something incredible is waiting to be known." And isn't that exactly what pulls us toward the stars? That unshakable feeling that there's more to existence than what we see from down here. Throughout history, humanity has looked up at the night sky with a mix of wonder, fear, and endless curiosity. We've told stories about the constellations, dreamed of touching the moon, and wondered if we're alone in this vast cosmic ocean. But it wasn't until we actually began to explore space that our understanding of ourselves and our place in everything truly began to shift. This video is about those moments, the ones that didn't just advance science or technology, but fundamentally changed us. We're going to explore 24 pivotal events in space exploration that reshaped human consciousness itself. From the first time we saw Earth hanging alone in the blackness of space to the stunning discovery of planets circling distant stars, each of these milestones stretched the limits of what we thought was possible. They challenged long-held beliefs, brought people together across borders, and ignited a deeper, more universal curiosity about who we are and why we're here. These weren't just achievements, they were awakenings. So join me on this journey through history as we revisit the moments that redefined what it means to be human. We'll see how each breakthrough, each leap into the unknown didn't just teach us about the universe, it taught us about ourselves. This is more than a story of rockets and missions. It's about perspective, humility, and the endless pursuit of understanding. And by the end, I think you'll see why looking outward toward the cosmos so often brings us closer to home. Think about the night sky for a moment. For all of human history, it was a canvas for myths and dreams, a distant, glittering ceiling we could watch but never touch. That all changed on one evening, October 4th, 1957. Without any grand announcement or fanfare, a small, polished metal sphere no bigger than a beach ball was lofted into the blackness by a Soviet rocket. They called it Sputnik 1, and as it slipped into orbit, it began to transmit a simple, steady signal back to Earth. A beep, beep, beep. This gentle, rhythmic sound, picked up by ham radios across the globe, was perhaps the most terrifying and exhilarating thing many people had ever heard. That humble beep represented a fundamental shift in human capability. For the first time ever, we had created something with our own hands that escaped our world entirely. It was a piece of technology, a human-made object circling our planet every 96 minutes. The notion that space was an unreachable frontier, a domain reserved for gods or science fiction, evaporated in that instant. Sputnik made it real. It was tangible proof that the cosmos was now within our grasp, and that realization sent shockwaves through governments, scientific communities, and the general public alike. Almost overnight, a fierce competition was born. The space race had begun, fueled by a potent mix of national pride, Cold War tensions, and sheer, unadulterated ambition. But beyond the politics and the competition, Sputnik did something even more profound to the human psyche. It triggered a deep, global introspection. People would go outside, look up at the stars, and know that something we built was up there, moving among them. It created a strange new blend of awe and anxiety, a sense of incredible achievement paired with the nervous understanding that the rules had changed forever. The sky was no longer a limit, it was a new ocean to be crossed. This moment marked the true dawn of the space age, shattering our Earth-bound perspective and forcing us to see our planet not as everything there is, but as a single world in a much larger, now accessible, universe. That small, beeping satellite didn't just open the door to space, it kicked it right off its hinges, setting the stage for everything that was to come. Just 27 years old at the time, Yuri Gagarin was more than just a pilot. He was humanity's first emissary to the stars. On April 12, 1961, strapped inside the Vostok 1 spacecraft, he was launched into a realm no person had ever visited. For 108 breathtaking minutes, he orbited our planet, a solitary human being witnessing what had, until that very day, been the exclusive domain of imagination. And what did he say when he looked out that tiny window? Not a technical report, not a status update. His words were simple, filled with genuine awe. "I see Earth," he reported. "It is so beautiful." That statement, so pure and unfiltered, did something profound. It gave us all a new set of eyes. For the first time, a member of our species was looking back at us, and what he saw wasn't a collection of separate countries or conflicting ideologies. He saw a single, stunningly beautiful planet, wrapped in oceans and clouds, without a single border visible from that incredible vantage point. This was the overview effect, experienced and articulated for the very first time. It was a perspective that instantly redefined home, transforming it from the street we live on into a fragile, isolated oasis hanging in the immense blackness of space. Gagarin's flight humanized the cosmos in a way Sputnik's beeps never could. It wasn't just that machines could survive out there, a person could. A man could eat, breathe, and function. He could feel wonder, he could thrive. This incredible leap shifted our collective consciousness from abstract theory to tangible, lived reality. Space was no longer a distant frontier for future generations. It was a place a person had just visited and returned from, smiling. Gagarin himself became a global symbol, not just of Soviet achievement, but of human courage and potential. His boyish grin and humble demeanor made him a relatable hero, proof that extraordinary bravery could reside in an ordinary person. This mission did more than advance technology. It expanded our concept of what is possible for humanity itself. It told every child on the planet that the sky was not the limit, it was the beginning. That powerful proof of concept that a human journey to space could begin and end safely set an irresistible precedent. It built a bridge of confidence, making the next logical step seem not just possible but inevitable. If one person could orbit the Earth, then surely we could soon set foot on another world. Imagine being on your way to another world for the very first time. That was the reality for the 3 astronauts of Apollo 8 in December of 1968. Their mission was a bold and dangerous one, to travel to the moon, orbit it, and return home. They were the first humans to ever leave Earth's orbit, the first to be truly, completely alone in the void, and as their spacecraft slipped around the far side of the moon, they lost all contact with home. For the first time in history, human eyes were seeing the lunar surface up close, a stark and barren landscape of craters and dust. But it was on their 4th orbit, as the command module came around the moon's horizon, that something unexpected and breathtaking happened. One of the astronauts, likely Bill Anders, glanced out the window and saw it. "Oh my God," he exclaimed. "Look at that picture over there, here's the Earth coming up." Wow, is that pretty? What they were witnessing was something no human had ever seen before, their own planet rising over the desolate, gray horizon of the moon. In a frantic, beautiful moment of shared awe, they scrambled for a camera. The first black and white shot was good, but they knew they needed color to capture the true majesty of the scene. Frank Borman handed Anders a roll of color film, and in that instant, one of the most profound photographs in human history was taken. The image shows a partial Earth, swirled with brilliant white clouds and deep blue oceans, hanging in the black emptiness of space above the lifeless, sun-bleached surface of the moon. It was a complete and utter reversal of perspective. For all of human existence, we had looked up at the moon. Now, for the first time, we were looking back at ourselves from its vantage point. This single photograph, this Earthrise, did more than just document a celestial event. It fundamentally rewired our collective consciousness. The sight of our world, so vibrant, so full of color and life, yet so small and isolated, struck a deep emotional chord across the globe. It was the ultimate lesson in scale and humility. In that image, there were no borders, no signs of war or conflict, no divisions of any kind, just a single, fragile oasis, a delicate blue marble suspended in an infinite and unforgiving darkness. It made our earthly squabbles seem suddenly trivial and insignificant, while simultaneously highlighting the incredible, precious beauty of our shared home. This visual proof of our planet's unity sparked a powerful global consciousness. It is no coincidence that the modern environmental movement found its footing shortly after this image was published. Seeing Earth as a finite, vulnerable system floating in the vastness of space made the need to protect it feel urgent and universal. The photo became an icon for peace, for global interconnectedness, and for a newfound sense of planetary stewardship. It influenced not just science, but art, philosophy, and culture, becoming a symbol of hope and a call for responsibility. That shift in perspective, from seeing ourselves as inhabitants of separate nations to citizens of a single planet, was a direct gift from the Apollo 8 mission. It prepared our minds for the even grander cosmic revelations that were soon to follow, reminding us that every great journey outward into the universe is also a journey inward, back to ourselves. But that stunning view of Earth from the moon was merely the prelude. The true crescendo of human ambition was yet to come, and it arrived just 7 months later. On July 20th, 1969, the entire world seemed to hold its breath. An estimated 600 million people, nearly a fifth of humanity at the time, were gathered around flickering television sets, their eyes fixed on grainy, black and white images being broadcast from 250,000 miles away. They watched as a spidery, fragile-looking spacecraft named Eagle descended toward a landscape no human had ever touched. Then came the voice, crackling with static but utterly calm. "Houston, Tranquility Base here. The Eagle has landed." A collective sigh of relief swept across the globe, but the real moment, the one we had all been waiting for, was still hours away. When Neil Armstrong finally backed out of the lunar module and began his careful descent down the ladder, he carried with him the hopes, dreams, and fears of all humankind. And then his boot made contact. "That's one small step for man," he said, the audio slightly garbled. "One giant leap for mankind." In that instant, something fundamental within our species shifted. We were no longer creatures bound to a single world. The moon, that ancient symbol of the unattainable, the object of our myths and lovesick poetry, was now a place where a human being could stand and leave a footprint. It was the ultimate testament to what we can achieve when we pool our knowledge, our courage, and our resources toward a common, seemingly impossible goal. This wasn't just an American victory, it was a human one. For a brief, shining moment, geopolitical tensions on Earth faded into the background, replaced by a shared planetary pride. The psychological impact was immeasurable. The moon landing shattered the ceiling of our aspirations. If we could do this, what truly was beyond our reach? It instantly fueled dreams of voyages to Mars and beyond, transforming science fiction into a plausible, achievable future. It forced a profound reflection on our place in the cosmos. Standing on another world and looking back at our own, we saw ourselves not as the center of the universe, but as participants in a much grander, infinite tapestry. We realized that this magnificent achievement, the culmination of centuries of scientific progress, was not an ending but a glorious beginning, the first page of a new chapter in our story. Yet, for all its triumph, this new era of exploration would also teach us that the cosmos is not always welcoming, and that reaching for the stars requires confronting sobering and sometimes terrifying realities. Just 3 days into their mission, with the moon growing larger in their windows, the routine calm of spaceflight was shattered by a sudden, violent bang. The Apollo 13 spacecraft shuddered. Warning lights lit up the command module like a Christmas tree. For a moment, astronauts Jim Lovell, Fred Hayes, and Jack Swigert simply stared at their instruments, trying to process the impossible. Then came the now immortal phrase, delivered with a stunning, almost surreal calmness. "Houston, we've had a problem." It wasn't a line from a movie script. It was the chilling, real-life announcement that a dream mission to the moon had just become a desperate, life-or-death struggle for survival 200,000 miles from home. An oxygen tank had exploded, critically damaging the service module and draining the spacecraft of its power, light, and most alarmingly, its breathable air. In an instant, the goal was no longer exploration. It was simply to get 3 human beings back to Earth alive. What followed was one of the most intense and collaborative rescue efforts in human history. The world watched, utterly gripped, as a team of engineers and flight controllers on the ground worked around the clock with the crew in space, improvising solutions to a cascading series of catastrophic failures. They had to figure out how to conserve power, how to scrub carbon dioxide from the air with makeshift filters built from spare parts, plastic bags, and duct tape, and how to navigate a cold, dark, and wounded spacecraft on a long, looping trajectory back to Earth. The lunar module, designed to support 2 men for 2 days on the moon's surface, suddenly became a tiny, fragile lifeboat for 3 men for 4 agonizing days. This crisis did something extraordinary to the global consciousness. National borders and political differences melted away. Soviet ships stationed themselves in the Pacific and Atlantic Oceans, offering assistance if needed. Countries around the world paused to offer support and prayers. For those tense 4 days, the entire planet was united not by a triumph, but by a shared, gut-wrenching vulnerability. We weren't watching superheroes, we were watching 3 ordinary men, relying on the collective brainpower and determination of thousands of others, fighting for every breath. This shared experience forged a deep, new empathy for the astronauts themselves. They were no longer distant, helmeted icons. They were husbands and fathers, freezing and exhausted, their fate hanging in the balance. Apollo 13 stripped away the glamour of spaceflight and revealed its stark, inherent danger. It was a sobering reminder that venturing into the cosmos is an inherently risky endeavor, a delicate dance on the very edge of human capability. Yet, in that sobering reality, we found our greatest strength. The successful splashdown was not just a victory for NASA, it was a victory for human ingenuity, for cool-headed problem solving under unimaginable pressure, and for the profound power of teamwork. It taught us that our greatest explorations are not defined by the absence of failure, but by our collective response to it. This hard-won maturity, this understanding that discovery and danger are inseparable partners, prepared our collective psyche for the next phase of exploration, not just visiting new worlds, but actively seeking answers to the most profound question of all, a question that would take us far beyond the confines of our own solar system. After the nerve-wracking drama of Apollo 13, which showed us the human cost of reaching into the void, our ambitions turned toward a question far older and more profound than simply planting a flag. We had proven we could go to another world. Now we wanted to know if we were the only ones there. This burning curiosity set its sights on our rust-colored neighbor, Mars. And in the summer of 1976, two robotic pioneers, the Viking 1 and Viking 2 landers, touched down on the Martian surface with a singular, monumental purpose: to perform the first ever experiments designed to detect life on another planet. This wasn't just another mission. It was a direct scientific assault on one of humanity's oldest and most fundamental mysteries. The design of these landers was a masterpiece of optimistic engineering. They weren't just geologic samplers, they were mobile biological laboratories, equipped with 3 intricate experiments crafted to sniff out the metabolic processes of Martian microbes. One experiment, called the labeled release, was particularly elegant. It offered a tiny soil sample, a nutrient cocktail tagged with a radioactive marker, then waited to see if any little Martian organisms would eat the meal and burp out a telltale radioactive gas. For a few exhilarating days, the data streaming back to Earth sent pulses of excitement through the mission control team. The experiment registered a positive result. A gas was being released. The collective breath of the scientific world hitched. Had we done it? Had we found our first evidence of life beyond Earth? But science, in its relentless pursuit of truth, rarely offers simple answers. Other experiments on the landers failed to find the organic molecules, the fundamental building blocks of life as we know it, that should have been present if biology was at work. The initial positive signal, many scientists eventually concluded, was likely caused by a surprising and exotic chemistry in the Martian soil, perhaps driven by powerful oxidants under the harsh ultraviolet light that bathes the surface. The final verdict was frustratingly, tantalizingly inconclusive. We had asked the universe a yes or no question, and it had responded with a mysterious, ambiguous shrug. Yet, to view Viking as a failure is to miss its earth-shattering importance entirely. For the first time in human history, we had seriously, scientifically, and directly posed the question, are we alone? To another world, this single act performed a profound alchemy on Mars itself. It was transformed forever in our minds from a distant, reddish point of light in the night sky, a symbol of war in ancient mythology, into a real place. A world with soil, with rocks, with a history, and with just maybe the potential for biology. Viking made the possibility of extraterrestrial life a legitimate subject for laboratory science, not just for philosophy or science fiction. This shift in thinking ignited fierce debates that raged through scientific conferences and spilled out into the public sphere. If life could arise independently on 2 different planets in one single solar system, what did that say about its prevalence across the galaxy? Were we living in a universe teeming with life, a cosmic garden? Or was Earth a miraculous, lonely oasis? Viking forced us to confront the possibility of our own cosmic mediocrity, or perhaps our incredible rarity. It blurred the line between science and philosophy, pushing us to consider humanity's role in a potentially inhabited cosmos. Were we the guardians of a unique spark, or simply one voice in a grand galactic chorus? By laying this crucial groundwork, by proving that the search was technologically possible and scientifically vital, the Viking missions became the direct ancestors of every rover and lander that has followed. They passed the torch, ensuring that the quest they began would continue, fueled by their ambiguous but world-altering data. Even as Viking was quietly listening for the whispers of life on Mars, another, far more ambitious project was being prepared for launch, one with a message for the distant and unknown future. The twin Voyager probes, set to embark on a grand tour of the outer planets, were marvels of scientific engineering, packed with instruments to unravel the mysteries of Jupiter, Saturn, and beyond. But their most profound cargo wasn't for collecting data, it was for giving it. Attached to each spacecraft side was a 12-inch gold-plated copper disc, a time capsule for the cosmos known as the Golden Record. This was not merely a scientific instrument, it was a deliberate, hopeful act of communication, a bottle cast into the cosmic ocean with a message inside. The very existence of these records represented a monumental shift in our motivation for exploration. We were no longer just going out to sea and to learn for our own benefit. We were now attempting to speak, to introduce ourselves to whoever or whatever might one day find these silent travelers drifting between the stars. This was a transition from a monologue to a potential dialogue, an expression of a deep, fundamental hope that we are not alone in the universe and a curiosity about what other forms of consciousness might exist. The project forced a small committee, led by the visionary astronomer Carl Sagan, to undertake a task of almost impossible profundity, to decide what to say on behalf of an entire species and planet. What is the essence of Earth? What defines humanity at its best? What is worth remembering about us? The contents of the record are a breathtakingly beautiful and humble answer to those questions. It contains 115 analog images depicting our anatomy, our DNA, our families, our architecture, and the staggering diversity of our natural world, from snowflakes to a breaching whale. It holds a 90-minute musical montage that spans the globe and the centuries, from the primal beats of Senegalese percussion and the soaring chants of Navajo night chants to the complex genius of Bach and the raw, universal blues of Chuck Berry's Johnny B. Good, there are natural sounds: the crash of ocean waves, the song of a humpback whale, the rumble of thunder, and the first cries of a newborn baby. And perhaps most movingly, there are spoken greetings in 55 languages, from ancient Akkadian to modern Wu, each one a simple hello from one individual of our world to an unknown neighbor in the void. Curating this collection was an act of radical global introspection. It demanded that we see ourselves not as separate nations or cultures, but as a single, interconnected civilization. The record doesn't hide our complexities or our struggles, but its overarching message is one of unity, creativity, and the shared, beautiful experience of being alive on a pale blue dot. It is a statement of who we hoped we were and who we aspire to be. This act of creating a legacy for the far future expanded our consciousness by reframing our place in the universe. We were no longer just explorers, we were participants, potential members of a wider cosmic community. It fostered a profound sense of humility. We are but one voice, sending a whisper into a vast and silent darkness, paired with an incredible sense of wonder at the sheer audacity of the attempt. The Golden Record is a testament to our boundless optimism, a message of peace and friendship destined to outlast our sun, carrying the best of who we are into the endless night. Yet, even as we sent our most hopeful message out into the void aboard Voyager, one of those very same spacecraft was preparing to send a message back to us, one of the most humbling and perspective-shattering images ever created. By 1990, Voyager 1 had completed its primary mission of exploring the outer planets and was speeding toward the edge of our solar system, over 6 billion kilometers from home. At the urging of the visionary astronomer Carl Sagan, scientists commanded the probe to perform one final task. They instructed it to turn its cameras around and take a last, parting photograph of the place it came from. What came back was not a dramatic, sweeping vista. It was a grainy, mostly black image dominated by bands of scattered sunlight, and there, almost lost in the vastness, was a tiny, faint speck of light, a pale blue pixel. That was us, that was Earth. Every human being who has ever lived, every triumph and every tragedy, every war and every work of art, every forest and every ocean, all of it contained within that single, barely their point of light. Sagan, upon seeing this image, was moved to write some of the most poignant words ever spoken about our place in the cosmos. He reflected, "Look again at that dot. That's here, that's home, that's us. On it everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. On a mote of dust suspended in a sunbeam. This was the ultimate exercise in scale and humility. The photograph provided irrefutable visual proof that our world is unimaginably small and isolated in the grand theater of the universe. It delivered a powerful blow to any remaining anthropocentric views, the idea that humanity is the central purpose of creation. From that distance, our national borders, our conflicts, our ideologies, none of it was visible. None of it mattered. The image argued, more convincingly than any philosophical treatise ever could, that the divisions we fight over are meaningless constructs when viewed from a cosmic perspective. It forged a new kind of consciousness, a cosmic awareness that we are all, irrevocably, in this together on a fragile spaceship hurtling through the void. The pale blue dot did not inspire despair at our insignificance, but rather a profound sense of responsibility. This was not a picture of meaninglessness, it was a picture of precious rarity. If this tiny speck is all we have, the only home we will ever know, then its care becomes our most sacred duty. The image became a foundational icon for the global environmental movement, a stark reminder that we have a collective obligation to protect the delicate, life-giving systems of our planet. It urged us to be kinder to one another, to cherish our shared existence on this pale blue dot, and to preserve it for all the generations yet to come. This humbling cosmic perspective, this breathtaking view from the outside looking in, prepared our minds for the next great revelation, one that would use powerful technology to look even deeper out into the universe, revealing not just our solitude, but the stunning abundance of everything else. After the humbling solitude of the pale blue dot, which showed us our lonely place in the cosmos, a new question naturally arose. If our world is just a speck, then what exactly is it a speck in? For centuries, astronomers had peered into the depths of space, but their view was limited, filtered, and blurred by Earth's turbulent atmosphere. They could see the bright, nearby galaxies, but they could only wonder what lay in the seemingly vast, empty blackness between them. Was it truly just void, or was our technology simply not powerful enough to see what was actually there? The launch of the Hubble Space Telescope in 1990 changed everything. Free from the distorting air of our planet, it promised clarity unlike anything we had ever achieved. But even its most optimistic designers could not have predicted the revolution that would come from a single, incredibly risky observation. In December of 1995, Hubble's controllers decided to point the powerful telescope at a patch of sky near the Big Dipper that was, by all previous accounts, utterly boring. For 10 consecutive days, a total of 140 hours, Hubble stared unblinking at a region of darkness so small it would appear like a grain of sand held at arm's length. It was a huge gamble, dedicating so much precious observation time to what many feared would be a picture of nothing. But when the light from that infinitesimal point of nothingness was collected and compiled, the result was not a dark, empty frame. It was a universe exploding with light. The Hubble Deep Field image revealed a staggering sight. Not dozens, not hundreds, but over 3,000 distinct galaxies, each a colossal island of billions of stars, all crammed into a fragment of sky that had previously been considered a blank canvas. The psychological impact of this image is almost impossible to overstate. It was a key that unlocked a door in our minds, revealing a universe of unimaginable vastness and complexity. Every single speck of light, every smudge and spiral in that photo was an entire galaxy, many of them as large or larger than our own Milky Way. And each of those galaxies contained hundreds of billions of stars, and around those stars there could be trillions of planets. The numbers were so colossal they ceased to be numbers and became a feeling, a profound, dizzying sense of scale that forever redefined our understanding of big. It made the pale blue dot feel even smaller, but in doing so, it made the cosmos feel infinitely more alive, more crowded, and more magnificent. We weren't just a speck in an empty void. We were a speck in an ocean of specks, a single thread in an impossibly rich and grand cosmic tapestry. This single image didn't just add to our knowledge, it fundamentally rewrote the textbooks. It provided undeniable visual proof that the universe was teeming with structure, that galaxies were not rare outposts but the fundamental building blocks of everything. It allowed astronomers to trace the evolution of galaxies across billions of years, seeing them in their infancy and watching them mature, providing a family photo album of the cosmos itself. The deep field was a powerful testament to human curiosity and ingenuity. It was an image born from a question, what's in the nothing, and a bold willingness to risk failure to find the answer. It demonstrated that the most profound discoveries often lie hidden in plain sight, waiting for us to develop the tools and the courage to look deeply enough. This incredible leap in our vision, this sudden understanding of the universe's true, crowded nature, inevitably led us to ask the next logical and perhaps most exciting question. If there are so many stars out there, could some of them have planets like our own? And if they do, could any of them be home to life? For centuries, the existence of planets around other stars was a matter of pure speculation, a comforting idea for science fiction, but without a single shred of proof. Astronomers had their theories, of course. It seemed logical that if our sun had a family of planets, then other stars should too, but logic isn't proof. For all we knew, our solar system could have been a bizarre, one-off cosmic accident. That all changed in October of 1995, when two Swiss astronomers, Michel Mayor and Didier Queloz, made an announcement that sent shockwaves through the scientific community. They had found something orbiting a sun-like star called 51 Pegasi, about 50 light-years away, but this was no ordinary planet. The data told a bizarre and unbelievable story. This world, which they named 51 Pegasi b, was a gas giant, a behemoth comparable to Jupiter. But unlike our Jupiter, which takes a stately 12 years to orbit the Sun at a safe, cold distance, this planet was tearing around its star in a blistering 4-day orbit. It was literally hugging its sun, a place where theory said a giant planet simply could not form. The discovery was so strange, so violently outside of every accepted model of planetary formation, that the initial reaction from many astronomers was deep skepticism, even outright disbelief. The data had to be wrong, it defied the rules, but as other teams confirmed the findings, that skepticism turned into a stunned, exhilarating realization. They hadn't found a weird exception, they had opened a floodgate. The message was clear and revolutionary: planets are not rare, they are everywhere. And they come in varieties so strange they had never even been dreamed of in our textbooks. This was the moment our consciousness shifted from asking if other worlds exist to knowing with absolute certainty that they do. The question was no longer, are there other solar systems, but what unimaginable kinds are out there? This single discovery ignited a gold rush in astronomy. New missions were designed, like the Kepler Space Telescope, which would go on to find thousands more by staring at a single patch of sky. watching for the telltale, minuscule dimming of a star as a planet crossed in front of it. The catalogue of alien worlds exploded, revealing a menagerie of cosmic weirdness. We found hot Jupiters like 51 Pegasi b, giant worlds boiling away in searing orbits. We found super-Earths, rocky planets larger than our own but smaller than Neptune, a whole new class of world that doesn't even exist in our own solar system. We found planets orbiting binary stars, just like Luke Skywalker's home planet Tatooine, making science fiction into science fact. We even found planets drifting alone in the dark space between stars, rogue worlds without a sun to call their own. This incredible diversity did more than just rewrite astronomy textbooks. It fundamentally expanded the human imagination. Suddenly, the possibility of life elsewhere wasn't just a philosophical debate, it was a statistical probability. Scientists began to identify planets sitting in the Goldilocks zone, the region around a star where temperatures might be just right for liquid water to exist on a planet's surface. We started analyzing the atmospheres of these distant worlds, using starlight filtering through their air to hunt for the chemical fingerprints of potential biology, like oxygen or methane. The search for life had a new, vast, and tangible hunting ground. This shifted our perspective on a deeply philosophical level. It challenged the long-held assumption of Earth's uniqueness, a concept known as the principle of mediocrity. Were we a common outcome of cosmic evolution, or are we still a rare and special fluke? The galaxy we now knew was teeming with possibilities, a cosmos filled with billions of potential homes for life, each with its own unique history and environment. This new reality also fueled practical ambitions. The discovery of so many nearby worlds made the dream of interstellar travel, once the domain of far future fantasy, feel slightly more tangible. We began to identify targets like the planets orbiting our closest stellar neighbor, Proxima Centauri. While the engineering challenges remain immense, knowing there are actual places to go makes the dream feel more urgent, more real. It encourages us to think not in terms of centuries, but in terms of millennia, to consider our legacy as a species that might one day step onto the shores of an alien world. The hunt for exoplanets transformed us from passive observers of the sky into active cartographers of a new frontier, mapping a galaxy that is far richer, stranger, and more inviting than we had ever dared to hope. This grand, statistical view of the cosmos, however, was about to be complemented by a much more intimate and personal form of exploration, as we sent our robotic ambassadors to trundle across the surface of our most tantalizing neighboring world. While our telescopes revealed a galaxy positively overflowing with alien worlds, our ambitions remained firmly rooted within our own solar system, focused on a world that has captivated humanity for millennia, the red, dusty globe of Mars. For centuries, it was a point of light, a god of war, a source of fantastical stories about canals and ancient civilizations. But in the 1990s, we decided to stop just looking and start truly visiting. We began sending our eyes, our ears, and our senses to crawl across its rusty soil. This new era of exploration didn't begin with a giant leap, but with a series of small, careful rolls. In 1997, a tiny, microwave oven-sized rover named Sojourner became the first of its kind, gingerly rolling down a ramp from the Pathfinder lander to become the first mobile explorer on another planet. It was a technology demonstration, a proof that we could remotely drive a vehicle on another world, and it captured the world's imagination, proving that exploration could be intimate, personal, and surprisingly relatable. But Sojourner was merely the opening act. The true revolution in our understanding of Mars began with the arrival of the twin rovers Spirit and Opportunity in January of 2004. Their mission was simple yet profound: to follow the water. These golf cart-sized robots were geologists on wheels, equipped with cameras, microscopes, and rock-grinding tools. And what they found in their years of incredible perseverance utterly transformed Mars in our minds. Opportunity, in particular, struck gold almost immediately, landing in a small crater where it quickly found bedrock that screamed with evidence of a watery past. It wasn't just a few puddles. The chemical and geological signatures pointed to an ancient environment where salty, acidic water had once flowed and pooled, an environment that could have been suitable for sustaining microbial life. Spirit, on the other side of the planet, found evidence of past hot springs and steam vents, environments that on Earth are teeming with extremophile life. These rovers did more than just collect data. They told a story. They sent back postcards from another world, panoramic images of rippling sand dunes, towering crater walls, and vast, empty plains under a pinkish-orange sky. They showed us sunsets on Mars, where the sun appears blue due to the fine red dust in the atmosphere, a sight of haunting, alien beauty. But perhaps their greatest gift was their personality. Managed by teams of dedicated engineers and scientists on Earth, these machines developed a character all their own. The world celebrated when opportunity got stuck in a sand dune and painstakingly worked its way free over weeks of careful maneuvering. We mourned when Spirit finally fell silent after years of service, and we were utterly inspired by opportunity, which was designed to last 90 days but kept exploring for over 14 years, finally succumbing to a planet-wide dust storm in 2018. Their perseverance in the face of immense challenges felt like a reflection of our own human spirit, a testament to our stubborn, enduring curiosity. The baton was then passed to a much larger, more sophisticated rover, Curiosity. This car-sized laboratory landed in 2012 with a breathtaking precision sky crane maneuver and one central question: could Mars have ever supported life? It wasn't just looking for water anymore, it was hunting for the building blocks of life itself. Drilling into ancient lakebed rocks in Gale Crater, Curiosity struck pay dirt. It discovered clear evidence of a past environment that was not only wet but also had the right chemical ingredients: carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, and, crucially, a chemical energy source that microbes could have used for food. It found complex organic molecules, the fundamental carbon-based compounds that are the essential ingredients for life as we know it. The verdict was in. Billions of years ago, Mars was a world with lakes, rivers, and all the necessary conditions to have supported living organisms. It wasn't just a barren rock, it was a world with a habitable past. This seismic shift in understanding made Mars feel tangible in a way it never had before. It was no longer a distant symbol or a scientific abstraction. It was a place with a history, a geology, and a story that we were actively piecing together. This tangible reality is what fuels the next great step. The latest rover, Perseverance, which landed in 2021, is built on this legacy. It is actively drilling and caching core samples from the very rocks that hold these secrets, samples that a future mission will hopefully bring back to Earth for detailed analysis. It even carries a tiny helicopter, Ingenuity, which proved that powered, controlled flight is possible in the thin Martian atmosphere, scouting the way for future explorers. These rovers have fundamentally bridged the gap between robotic reconnaissance and human exploration. They have mapped the terrain, analyzed the soil for toxins, and even tested a device to produce oxygen from the Martian atmosphere. They are the advanced scouts doing the groundwork for the day when human footsteps will be pressed into that red dust. This progression from myth to reality has ignited a global conversation about our future on Mars. The question is no longer can we go, but should we go, and what will it mean when we do? We debate the ethics of planetary protection, concerned about contaminating a world that might still harbor its own native microbial life. We grapple with the immense technological and physiological challenges of keeping humans alive on a cold, radiation-blasted world for years at a time. And we are forced to consider the social and philosophical implications of becoming a multi-planetary species. Will it be a story of heroic expansion and a hedge against extinction, or one of colonial repetition on a new frontier? The Mars rovers, through their quiet, diligent work, have given us the knowledge to have these debates not as science fiction, but as a coming reality. They have made Mars a destination, a real place on a map that we are now seriously planning to visit. And as we look at the data from these intrepid robots, we realize that the next great discoveries in our solar system may not be on planets at all, but on the icy, enigmatic moons orbiting the gas giants, worlds that hide vast, secret oceans beneath their frozen crusts. While our rovers were busy mapping the ancient, dried-up riverbeds of Mars, a different kind of explorer was revealing an entirely new category of world, one that defied every expectation we had about what a moon could be. The Cassini-Huygens mission, a monumental collaboration between NASA, the European Space Agency, and the Italian Space Agency, arrived at the Saturn system in 2004. It wasn't just going to orbit the planet and take pretty pictures. It was embarking on a 13-year grand tour, a deep and intimate study of a complex planetary family. And what it found there would forever change our definition of a habitable world, pushing it far beyond the familiar concept of a planet orbiting at just the right distance from its sun. The crown jewel of this mission was the deployment of the Huygens probe toward Saturn's largest moon, Titan. On January 14, 2005, Huygens began its daring descent through a thick, orange, and completely opaque atmosphere. For 2.5 hours, it parachuted down into the unknown, its sensors frantically tasting the air and its camera seeing nothing but haze. Then, finally, the haze cleared, and the first images from the surface of another moon began to stream back to Earth. They revealed a landscape that was hauntingly, bizarrely familiar. There were river channels, drainage networks, and shorelines. There were rocks, rounded and smoothed as if by a flowing liquid. But the chemistry was all wrong, a surreal parody of Earth. The temperature is -290 degrees Fahrenheit. The rocks are made of water ice as hard as granite. And the liquid that carved those channels and filled those lakes isn't water. It's liquid methane and ethane, hydrocarbons that rain from the sky and flow across the landscape in an alien hydrological cycle. Huygens had landed on a damp, pebbly plain, becoming humanity's first emissary to a world with a complex weather system entirely separate from our own. This was the moment our consciousness expanded to fully embrace moons as destinations, as complete and complex worlds in their own right. Titan was no longer just a moon, it was a time capsule, a frozen analog of a very early prebiotic Earth preserved in deep freeze. Its thick atmosphere, rich in organic chemistry, is a laboratory for the same kinds of chemical reactions that likely occurred on our planet billions of years ago before life ever emerged. It forced us to ask a revolutionary question: could life, using liquid methane the way we use water, potentially arise in such an environment? The very possibility stretched the boundaries of biology itself, suggesting that life might be more inventive and resilient than we had ever conceived. But Cassini's revelations didn't stop with Titan. As the spacecraft continued its orbits, it turned its instruments toward a much smaller, icy moon named Enceladus. To everyone's astonishment, Cassini discovered that this seemingly pristine, gleaming white world was dramatically active. Gargantuan plumes of water vapor and ice were erupting from a series of massive fissures near its south pole, shooting material hundreds of miles into space. This wasn't a dead ball of ice. It was a world with a subsurface, global ocean of liquid water, heated and churned by the gravitational tug of war with Saturn. Cassini didn't just see these plumes. On a daring dive through one of them, it directly sampled their composition. The analysis was breathtaking. The plumes contained water vapor, salts, silica nanoparticles, and a suite of organic molecules including methane, carbon dioxide, and propane. Most crucially, they found molecular hydrogen, a key chemical energy source that, on Earth, supports entire ecosystems of microbes living around hydrothermal vents on the dark ocean floor. The implications were staggering. Enceladus, a moon just 300 miles wide, possessed all three of the essential ingredients for life as we know it: liquid water, a rich mix of organic building blocks, and a source of chemical energy. It didn't need to be in the Goldilocks zone around the Sun. It had created its own habitable environment through internal heat. This discovery single-handedly rewrote the astrobiological playbook. It meant that habitable real estate in our solar system, and by extension the universe, could be far more abundant than we ever dreamed. We no longer needed to look just at planets. We had to look at the vast number of icy moons orbiting gas giants, each one a potential haven for life, warmed from within. Cassini's final act was a testament to its incredible success and the thirst for knowledge it inspired. In 2017, with its fuel nearly exhausted, scientists deliberately guided the spacecraft on a series of daring rings between Saturn's rings and the planet itself, gathering unprecedented data before commanding it to plunge into Saturn's atmosphere, ensuring it would never accidentally contaminate a pristine moon like Enceladus or Titan with Earth microbes. Its mission may have ended, but its legacy is brighter than ever. The discoveries at Enceladus and Titan have directly spawned a new generation of missions now in development. Dragonfly, a nuclear-powered drone, will soon fly through Titan's thick atmosphere, landing on its organic sand dunes to search for the chemical precursors of life. Proposals are underway to send probes to fly through the plumes of Enceladus, perhaps even with instruments capable of directly detecting signs of living organisms. Cassini taught us to look at the frozen, outer reaches of our solar system not as a barren wasteland, but as a potential sanctuary, a place where the secret to life's beginnings, or perhaps even its contemporary existence, might be waiting, hidden beneath a shell of ice. For a full century, it existed only as a beautiful, untested idea in the pages of Albert Einstein's theory of general relativity. He proposed that the universe has a fabric, a four-dimensional tapestry called space-time, and that the most violent events in the cosmos, colliding black holes, exploding stars, would send ripples through this fabric, much like a pebble dropped in a pond. These ripples were gravitational waves, but Einstein himself was skeptical we could ever detect them. They would be infinitesimally small, distorting the very fabric of reality by a distance thousands of times smaller than the nucleus of an atom. To find them would require not just incredible technology, but near superhuman patience. Then, on September 14, 2015, after decades of searching, it happened. A signal lasting less than half a second swept through the twin observatories of LIGO in Louisiana and Washington State. It was a perfect rising chirp, a cosmic melody played on the strings of space-time itself. The source, two black holes, each about 30 times the mass of our Sun, locked in a final, fatal dance over 1.3 billion years ago, merging into a single, more massive whole and converting a portion of their mass into pure energy in the form of these waves. This detection did far more than just confirm a prediction. It fundamentally changed how we perceive the universe. Until that moment, all of astronomy had been based on light. We looked at the cosmos. We built telescopes to collect every form of electromagnetic radiation, from radio waves to gamma rays, but this was different. LIGO didn't see anything, it heard. For the first time in human history, we were listening to the universe. This was the dawn of a completely new sense, allowing us to perceive events that are utterly dark, completely invisible to any telescope. The collision of two black holes, for instance, emits no light at all. It is a transaction that happens in perfect, silent darkness, but it screams its presence through gravitational waves. This new sense opened a window onto the most energetic and secretive phenomena in existence, letting us tune into the hidden symphonies of the cosmos. The philosophical impact was immediate and profound. It was a stunning validation of human intellect, a concept dreamed up by one man 100 years prior, using only thought and mathematics, had been proven correct with breathtaking precision. It underscored the deep, underlying interconnectedness of everything, showing that space and time are not a static stage upon which events unfold, but a dynamic, flexible entity that can be stretched, squeezed, and set ringing by the motions of mass. We weren't just learning about black holes, we were learning about the very nature of reality. This breakthrough also stood as a monumental testament to international collaboration. LIGO is the result of work by over 1,000 scientists from more than 20 countries, a decades-long effort requiring unprecedented levels of precision and dedication. It proved that humanity, when united by a common, curious goal, can achieve the seemingly impossible. This new era of so-called multi-messenger astronomy reached its first crescendo just 2 years later, in 2017. This time, LIGO detected the ripples from the collision of two neutron stars, the incredibly dense, city-sized corpses of exploded stars. Crucially, this cataclysm did produce light. The alert went out to astronomers worldwide, and within hours, every major telescope on Earth and in space swiveled to look at that single patch of sky. They saw the brilliant glow of newly forged gold, platinum, and other heavy elements being cast out into the universe, solving the long-standing mystery of where these precious metals are created. For the first time, we had both heard the event and seen its brilliant aftermath. We were no longer just observers, we were witnesses to the full story, able to piece together the narrative of cosmic creation using both sound and sight. This powerful new way of investigating the universe promises even more startling revelations, allowing us to probe the moments after the Big Bang itself, and perhaps even uncover the nature of the dark energy that is pulling the cosmos apart. While we were learning to listen to the cosmic symphony of colliding black holes, another mission was undertaking a different kind of intimate exploration, one that required not just hearing but touching. For centuries, comets had been objects of superstition and fear, celestial apparitions seen as portents of doom or divine messages. Even as science demystified them as icy wanderers from the outer solar system, they remained distant, fleeting specters, their secrets locked away. The European Space Agency's Rosetta mission aimed to change that forever. Its goal was as ambitious as it was unprecedented: to not just fly by a comet, but to chase one down, orbit it, and land a probe on its surface. The target was Comet 67P Churyumov-Gerasimenko, a lumpy, duck-shaped relic measuring just about 2.5 miles across. After a decade-long journey through the solar system, the Rosetta spacecraft finally reached its target in 2014. What it found was a world of stunning and unexpected complexity. This was no simple dirty snowball. Rosetta's cameras revealed a dramatic landscape of towering cliffs, deep pits, and vast, dusty plains. But the real prize was yet to come. On November 12, 2014, the world watched with bated breath as the small Philae lander was dispatched from the orbiter to make the first ever controlled landing on a comet's nucleus. The descent was perfect, but then fate intervened. Philae's harpoons, designed to anchor it to the surface, failed to fire. The lander bounced not once but twice, soaring across the landscape for 2 hours before finally coming to rest in a shadowy crevice tilted on its side. It was a precarious situation, limiting the lander's access to sunlight to power its solar panels. Yet, even in its compromised state, Philae's 60 hours of battery life were a whirlwind of scientific triumph. The data it sent back was nothing short of revolutionary. Its instruments drilled into the comet's surface and sampled its composition, and the findings were profound. They detected a suite of 16 organic compounds, including 4-methyl isocyanate, acetone, propionaldehyde, and acetamide, that had never been found on a comet before. Most significantly, they found the amino acid glycine, a fundamental building block of proteins and therefore life. They also found phosphorus, a key component of DNA and cell membranes. This was a monumental discovery. It provided the strongest evidence yet that comets could have been the delivery vehicles that brought the essential ingredients for life to the early Earth. The water on 67P also told a story. By analyzing the ratio of heavy water containing a heavier form of hydrogen called deuterium, scientists found it didn't match the water in our oceans, challenging the long-held idea that comets alone supplied Earth's water. This suggested a more complex history, perhaps with asteroids playing a major role. The mission transformed comets in our collective consciousness. They were no longer just beautiful, icy ghosts in the night sky. They were revealed as ancient time capsules, pristine leftovers from the formation of the solar system 4.5 billion years ago. By landing on one, we were effectively touching the original building blocks from which our entire planetary system was constructed. This created a powerful, tangible connection to our cosmic origins. We weren't just looking at a distant object, we were interacting with a piece of our own history, a messenger from the era of planetary birth. The Rosetta mission also captured the global imagination in a uniquely modern way. The European Space Agency ran a brilliant social media campaign, personifying the spacecraft and lander, giving them voices and personalities. Millions of people followed the anxious wait during Philae's descent and celebrated its landing using the hashtag #CometLanding. When the lander's fate became uncertain, the public shared in the drama and the hope. When it fell silent, there was a palpable sense of loss. And when the Rosetta orbiter finally found Philae's final resting place in a dark crack just weeks before the mission ended, it provided a poignant and satisfying conclusion to the story. This humanization of a robotic mission made the science feel personal and accessible. It wasn't just data, it was an adventure we all followed together. Rosetta's final act, a controlled impact onto the comet's surface in 2016, was a fitting end to a mission that brought us closer to the raw materials of the cosmos than ever before. It gave us a new appreciation for these primitive bodies, not as threats or omens, but as cherished storytellers holding the secrets to our own beginnings. This intimate study of an ancient building block from our own solar system's backyard naturally made us yearn to explore even farther out, to the dim, frozen frontier where even more primordial objects reside, waiting to tell their stories. For decades, Pluto was the enigmatic ninth planet, a faint and fuzzy speck in even our most powerful telescopes. It was a beloved underdog, the quirky outsider of our solar system that had captured the public's imagination since its discovery in 1930. Then, in 2006, in a move that shocked and saddened many, the International Astronomical Union made a controversial decision, reclassifying Pluto as a dwarf planet. It was demoted, stripped of its planetary status based on new scientific criteria. To much of the world, it felt like a loss, a shrinking of our cosmic neighborhood. But science, in its relentless pursuit of understanding, had a surprise in store. We hadn't truly met Pluto yet, and on July 14, 2015, after a 9-year, 3-billion-mile journey, NASA, a New Horizons spacecraft, screamed through the Pluto system at 36,000 miles per hour, and in a breathtakingly short flyby, gave us our first proper introduction. The images that slowly trickled back to Earth over the following days and weeks were nothing short of mind-blowing. This was not the dead, boring ice ball many had expected. New Horizons revealed a stunningly complex and vibrant world. The first close-up showed a vast, heart-shaped plain of nitrogen ice, instantly becoming one of the most recognizable features in the solar system. But the surprises kept coming. This tiny world, so far from the sun's warmth, had water ice mountains as tall as the Rockies, but because of the low temperatures, that water ice is as hard as bedrock. Most astonishingly, there were no craters on that heart-shaped plain, named Tombaugh Regio after Pluto's discoverer. This was a monumental discovery. A lack of craters means the surface is geologically young. Something had resurfaced it, erasing the scars from ancient impacts. But what could possibly provide the energy for such activity on a small, frozen world at the very edge of our solar system? The answer seemed to point to something scientists could barely believe: the possibility of a subsurface ocean of liquid water, kept from freezing by the heat from the radioactive decay of rocks in Pluto's core. This notion was supported by other bizarre features, like possible cryovolcanoes, ice volcanoes that might erupt with a slushy mix of water, ammonia, and methane instead of molten rock. The spacecraft also revealed Pluto's thin but complex atmosphere and its system of 5 moons, including the giant Charon, which is so large relative to Pluto that they orbit a point in space between them, making them a binary system dancing through the darkness. Every single piece of data painted a picture of a dynamic, active, and bewilderingly diverse world. The old, simple narrative of our solar system, with its neat categories of inner rocky planets and outer gas giants, completely fell apart. Pluto, and by extension the entire Kuiper belt it represents, is a third domain, a realm of icy dwarfs that are every bit as complex and fascinating as any planet. This revelation did more than just rewrite textbooks. It performed a subtle but powerful alchemy on the public consciousness. The flyby tapped into a deep well of nostalgia and affection for the little world that could. People who had felt a sense of loss at its demotion now felt a new sense of pride and wonder. Pluto wasn't less than a planet. It was the king of something new, the first example of an entire class of worlds we were just beginning to understand. It was a triumphant underdog story, a testament to the idea that you don't have to be the biggest to be breathtakingly interesting. The mission became a cultural event, a shared moment of discovery that reminded everyone why we explore. More importantly, the New Horizons Flyby delivered a profound lesson in intellectual humility. It was a stark, beautiful reminder that our scientific classifications are just that human-made boxes we try to fit the universe into. The universe, in its infinite creativity, constantly defies our neat categories. True exploration means being willing to have our preconceptions shattered, to replace certainty with a more vibrant and exciting curiosity. By venturing to the very edge of our known solar system, New Horizons didn't show us an ending point, it showed us a new beginning. It revealed that the Kuiper belt is a vast, unexplored frontier filled with thousands of similar icy worlds, each with its own stories to tell. This push into the deepest, darkest reaches of our own celestial neighborhood reminds us that the influence of our sun, both gravitationally and through its faint solar wind, extends far beyond what we can see, shaping a region we are only just beginning to map. After journeying to the frozen, primordial edges of our solar system with new horizons, we now turn our attention inward toward the brilliant, life-giving heart of our cosmic neighborhood, the Sun. For all of human history, our star has been a constant, a dependable presence in the sky that we often take for granted. We rely on its light and heat for our very existence, yet its inner workings have remained shrouded in mystery, its violent outer atmosphere an enigma that defied close observation. That all changed on August 12, 2018, with the launch of a daring mission that reads like something from science fiction. The Parker Solar Probe, a spacecraft designed not just to study the Sun from a distance, but to literally touch it. The mission's goal is as straightforward as it is audacious: to solve two long-standing mysteries about our star. First, why is the Sun's corona, its wispy, outer atmosphere, millions of degrees hotter than its visible surface below? This defies all basic logic, like a flame feeling hotter the farther you get from the fire. Second, what exactly accelerates the solar wind, that relentless supersonic stream of charged particles that constantly blows off the Sun and bathes the entire solar system? To find the answers, the Parker probe had to do what no spacecraft had ever done before: fly through the corona itself. This required an incredible feat of engineering and navigation. The probe is on a series of ever-tightening orbits around the Sun, using Venus's gravity as a brake to gradually swing it closer and closer to the solar inferno. On its final orbits, it will come within a mere 3.8 million miles of the Sun's surface, traveling at a staggering 430,000 miles per hour, fast enough to fly from New York to Tokyo in under a minute. To survive this hellish environment, the probe is equipped with a revolutionary heat shield called the Thermal Protection System. This 4.5-inch thick carbon composite shield is like a high-tech sandwich plate that faces temperatures exceeding 500 degrees Fahrenheit, all while keeping the spacecraft's payload comfortably at room temperature behind it. Even the probe's solar panels are ingeniously designed to retract into the shadow of the shield during its closest approaches, with just a tiny portion peeking out to generate power while being cooled by circulating water. Every aspect of its design is a testament to human ingenuity in the face of a seemingly insurmountable challenge. The very existence of this mission shifts our consciousness, transforming the Sun from a distant, abstract ball of light into a dynamic, physical place that we can actively explore and touch. It embodies a new level of cosmic intimacy, proving that even the most formidable forces of nature can be studied up close with enough courage and cleverness. The data already streaming back from the Parker probe has been nothing short of revolutionary. It has flown through the birthplace of the solar wind, identifying specific structures in the Sun's magnetic field, called switchbacks, that act like giant accelerators, flinging particles outward at incredible speeds. It has sampled the dust-free zone around the Sun, confirming theories about the vaporization of interstellar material, and has provided our first ever direct measurements of the plasma and magnetic fields within the corona. This isn't just abstract science, it has direct, profound implications for life on Earth. The solar wind and larger eruptions like coronal mass ejections can create devastating space weather. These events have the power to knock out satellites, disrupt GPS and radio communications, and even induce massive electrical currents in power grids on the ground, causing continent-wide blackouts. A famous example is the Carrington event of 1859, a solar storm so powerful it caused telegraph systems across Europe and North America to fail, with operators receiving shocks and pylons throwing sparks. A similar event today in our hyper-connected, electricity-dependent world could cause trillions of dollars in damage and take years to recover from. By understanding the fundamental physics of how these storms are born, the Parker Solar Probe is essentially giving us a forecast not just for space weather, but for the security of our technological civilization. It allows us to move from being passive victims of the sun's tantrums to informed planners who can better shield our infrastructure and shut down vulnerable systems before a storm hits. This mission powerfully links our daily, earthly existence to the grand, chaotic processes of our star, reminding us that we are not separate from the cosmos but are living within the extended atmosphere of an active and sometimes tempestuous star. Furthermore, the knowledge gained doesn't just apply to our sun. The Parker Probe is in effect a mission to every star. The processes it is studying, coronal heating, stellar winds, magnetic activity, are universal. By unraveling the mysteries of our own familiar star, we gain a Rosetta Stone for understanding the billions of other stars throughout the galaxy, learning how they evolve and how they influence their own families of planets. This incredible journey to our celestial anchor prepares us to appreciate the next great leap in our vision, a monumental achievement that required turning our entire planet into a single, giant telescope to capture the uncapturable. For over a century, black holes existed as the ultimate cosmic paradox, a place where the known laws of physics seemed to break down, a prediction so extreme that even Einstein doubted they could be real. They were the universe's most perfect secrets, objects with gravity so intense that not even light could escape their grip, rendering them fundamentally invisible, undetectable by any conventional means. They were the realm of pure theory, the subject of complex equations and thought experiments, but never something we could actually see. All of that changed on April 10, 2019, when a team of scientists from the Event Horizon Telescope project held press conferences simultaneously on 6 continents to unveil an image that many believed was impossible to obtain. There, on screens around the world, was a lopsided, fiery ring of light encircling a perfect sphere of utter darkness. It was the shadow of the supermassive black hole at the heart of the galaxy Messier 87, a gravitational monster weighing in at 6.5 billion times the mass of our Sun. The creation of this image was a feat of such staggering ambition and global cooperation that it almost defies belief. The Event Horizon Telescope wasn't a single telescope. It was a virtual instrument the size of our entire planet, created by synchronizing 8 of the world's most powerful radio observatories from the peaks of Hawaiian volcanoes to the high deserts of Chile and the frigid landscapes of the South Pole. For several days in April of 2017, these far-flung facilities all turned their enormous dishes toward the same point in the sky, collecting waves of light emitted by the superheated gas swirling around the black hole. The amount of data they gathered was so immense it couldn't be sent over the internet. It had to be physically flown on hundreds of hard drives to central processing centers in the United States and Germany. There, supercomputers and a team of over 200 scientists worked for 2 years to carefully piece together the information, like assembling a cosmic jigsaw puzzle with 1 billion pieces, to finally develop this single, historic image. The psychological impact of seeing this image was immediate and profound. A black hole was no longer just an abstract concept or a menacing plot device in a science fiction movie. It was a real physical object, a place in the universe that we could point to and say, there it is. This visual confirmation did more than just validate a century of theoretical physics. It made the incredible tangible. It allowed the human mind to finally grasp something that was previously ungraspable. The glowing ring we see isn't the black hole itself, but the photon ring, the very last place where light can still orbit the black hole before being lost forever to the event horizon, the point of no return. The dark void at the center is the shadow of the black hole's event horizon, cast against this brilliant backdrop of light, a silhouette of the most extreme gravitational environment in the universe. This achievement was a monumental testament to what humanity can accomplish when we work together across borders, cultures, and disciplines. The collaboration involved scientists from over 20 countries and 60 institutions, a global brain trust united by a single, shared question. In an era often defined by division and conflict, this project stood as a brilliant counterpoint, a reminder that our curiosity and our capacity for wonder are universal traits that can bring out the very best in us. It showed that no scientific challenge is too great when we pool our resources, our intellect, and our determination. The image itself instantly became a cultural icon, appearing on everything from newspaper front pages to T-shirts and memes. It inspired artists, musicians, and philosophers, sparking new conversations about the nature of reality, the limits of human knowledge, and our place in a universe that contains such terrifying and beautiful wonders. Scientifically, the image was a goldmine. It provided powerful new evidence supporting Einstein's theory of general relativity, showing that the predicted shape and size of a black hole's shadow matched the equations with stunning accuracy, even under these most extreme conditions. It gave astronomers a new tool to study the chaotic dynamics of accretion disks, the whirling storms of superheated gas and dust that feed these cosmic beasts. But perhaps its greatest gift was the doorway it opened. This was not the end of a journey, but the beginning of a whole new field of observational black hole physics. The Event Horizon Telescope collaboration is already adding more telescopes to its network, sharpening its vision to create even clearer movies of black holes in action, hoping to capture the turbulent flow of material in real time. This first image proved it was possible, transforming black holes from mythical monsters into observable laboratories for testing the laws of physics at their very limits, inviting us to ask even deeper questions about the fabric of space-time and the ultimate fate of matter. For decades, the monumental cost of reaching orbit was the single greatest barrier standing between humanity and the stars. Building a rocket was a bit like commissioning a magnificent, custom-built skyscraper, only to push a single button and watch the entire multi-billion-dollar structure collapse into the ocean after just one use. It was an inherently wasteful and staggeringly expensive process, a financial gravity well that kept spaceflight firmly in the hands of a few government agencies. The idea of reusing a rocket the way we reuse an airplane seemed like a distant fantasy, an engineering puzzle too complex to solve. Then, on a clear December evening in 2015, that fantasy became reality. A SpaceX Falcon 9 rocket, after successfully delivering 11 satellites to orbit, performed a series of breathtaking maneuvers. It flipped around, reignited its engines to slow its suicidal descent, and descended back through its own exhaust plume toward a landing pad at Cape Canaveral. For a few heart-stopping seconds, it hovered perfectly, a 16-story building balancing itself on a spear of fire before gently touching down. The crowd at Mission Control erupted in cheers. For the first time in history, an orbital-class rocket had returned from space and landed vertically, intact and ready to fly again. This was not a one-off stunt. It was the culmination of years of iterative and very public trial and error. SpaceX had embraced a philosophy of rapid prototyping, launching, and yes, even blowing up rockets to gather the data needed to solve this immense challenge. They live-streamed every attempt, turning potential failures into a shared global learning experience. The world watched as early boosters would land, only to tip over and explode on the deck of their drone ship landing platforms. Each fiery crash was met not with despair but with the determined phrase, rapid unscheduled disassembly, followed by a commitment to try again. This transparent, iterative approach did something crucial. It made the process of radical innovation feel human, relatable, and achievable. It wasn't a secret government project happening behind closed doors. It was a scrappy, entrepreneurial effort playing out in real time for anyone with an internet connection. When that first landing finally succeeded, it felt like a victory for the underdog, a triumph of tenacity that belonged to everyone watching. The psychological shift this caused cannot be overstated. It fundamentally rewrote the business case for space. Reusability slashed the cost of access to orbit by orders of magnitude. Suddenly, launching satellites, sending cargo to the International Space Station, and even planning new missions became dramatically more affordable. This democratization of space opened the floodgates for a new ecosystem of commercial activity. Small startups could now dream of building constellations of internet satellites. Universities and research institutions could afford to send experiments into orbit. The arena of space was no longer an exclusive club for superpowers. It had become a new frontier for commerce, innovation, and private ambition. This shift in consciousness reframed space exploration from a purely scientific or nationalistic endeavor into a potential economic engine, a place where businesses could thrive and create new industries. This new, sustainable model also forced a critical reevaluation of how we treat the space environment. The image of a rocket landing gracefully instead of plunging into the ocean to become marine debris was a powerful symbol of a more responsible approach. It championed the idea that our expansion into the cosmos shouldn't be a path littered with the ghostly shells of discarded machinery, but a deliberate, reusable, and circular infrastructure. This ethos of iteration, of learning from each flight to make the next one better and safer, mirrors the development of aviation in the early 20th century. Each landed booster is not just a saved asset, it is a data goldmine, providing engineers with invaluable information on the wear and tear of actual flight, enabling them to continuously refine and improve the technology. This creates a virtuous cycle where success builds upon success, accelerating progress at an unprecedented rate. Perhaps the most profound cultural impact has been the rebirth of public engagement. SpaceX's live streams, with their cinematic views of Earth from space, the pulse-pounding tension of the landing burns, and the triumphant sight of a soot-stained booster standing proudly on the launch pad, have turned rocket launches into must-see global events. They have humanized spaceflight once more, making it feel immediate, exciting, and accessible. That iconic image of a rocket landing on a drone ship, dubbed, "Of Course I Still Love You," is a symbol of a new, optimistic, and ambitious future. It has inspired a new generation of engineers, scientists, and dreamers who see space not as a distant government program, but as a place they can actively help build. This entrepreneurial spirit, this fusion of cutting-edge engineering with a bold vision for the future, has completely reshaped the landscape of space exploration, proving that with innovation and determination, the sky is not the limit. It's just the beginning of a new, sustainable pathway to the stars. But this new era of commercial access and reusable rockets is about more than just lowering costs and inspiring dreams. It's creating the crucial infrastructure needed for humanity's next giant leap, a return to the moon that is not about leaving flags but about building foundations. The Apollo program was a magnificent sprint, a breathtaking display of national will that proved we could go to the moon. the Artemis program, named after the twin sister of Apollo in Greek mythology, is something entirely different. It is designed to be a marathon, a sustainable and deliberate effort to not just go back, but to stay. Its core mission is to establish a long-term human presence on the lunar surface, using it as a proving ground for the technologies, the techniques, and the human endurance required for the ultimate goal, sending astronauts to Mars. This shift in purpose fundamentally reframes the moon in our collective consciousness. It is no longer a finish line, a trophy to be won and then abandoned. Under Artemis, the moon becomes a workshop, a construction site, a scientific laboratory, and a vital waypoint. It is the cosmic backyard where we will learn how to live and work effectively in a deep space environment. We will practice using local resources, a concept called in situ resource utilization, by extracting water ice from permanently shadowed craters to create drinking water, breathable air, and even rocket fuel. We will learn to build habitats that can protect crews from the moon's harsh radiation and micrometeorite impacts. Every lesson learned, every problem solved on the lunar surface, is a direct rehearsal for the far greater challenges of a multi-year mission to the Red Planet. This vision expands our ambition from brief visits to permanent settlement, transforming our relationship with space from one of exploration to one of inhabitation. Another profound evolution embodied by Artemis is its spirit of collaboration. Unlike the Apollo program, which was largely a national competition against a rival superpower, Artemis is being built as a global village. NASA has established the Artemis Accords, a set of principles for peaceful and cooperative space exploration that has already been signed by dozens of nations, from traditional space powers like Canada, Japan, and European nations to emerging players like the United Arab Emirates and Brazil. These international partners are not just signing a document, they are contributing critical hardware. The European Service Module provides power and propulsion for the Orion spacecraft. Canada is building a sophisticated robotic arm for the Lunar Gateway, a small space station that will orbit the moon and serve as a staging post for sorties to the surface. Japan is developing a pressurized rover for astronauts to explore the lunar terrain. This model recognizes that the scale of this endeavor is too vast, too expensive, and too important for any single nation to undertake alone. It frames space exploration not as a national achievement, but as a shared human project, fostering a sense of global unity and common purpose that is desperately needed on Earth. Perhaps the most powerful and conscious shift Artemis represents is its commitment to inclusivity. The program has explicitly pledged to land the first woman and the first person of color on the lunar surface. This is far more than a symbolic gesture. It is a monumental statement about who gets to participate in the next chapter of the human story. For decades, the iconic image of an astronaut has been a white man in a bulky suit. Artemis is consciously, deliberately rewriting that iconography for the 21st century. It sends an unequivocal message to every young girl and every child from an underrepresented background that space belongs to them too. It ensures that the future we are building beyond Earth reflects the beautiful diversity of the species building it. This commitment is already having a tangible impact, inspiring a new, broader generation of students to pursue studies in science, technology, engineering, and mathematics, knowing that the door to the cosmos is finally open for them. The architecture of Artemis itself is a testament to this new, multifaceted approach. It leverages the innovation of commercial partners like SpaceX, which is developing the Starship human landing system, and combines it with NASA, a deep experience in deep space mission design. The program will utilize the powerful new Space Launch System rocket, the Gateway Station, and the Orion spacecraft, creating a flexible and reusable transportation system between Earth and the Moon. This public-private international partnership model is the blueprint for the future of space exploration, one that is more resilient, more innovative, and more sustainable than anything that has come before. Artemis is not a nostalgic retread of past glories. It is the foundational first step toward a future where humanity is no longer confined to a single world, a future where the Moon is our first outpost on the frontier and a constant reminder of what we can achieve when we choose to go together. Yet, even as we build the partnerships and the architectures for human return to the Moon, our most advanced robotic geologist is already hard at work on the surface of Mars, undertaking a mission of such profound ambition that its full payoff will require an entire decade of meticulous effort and international collaboration. The Perseverance rover, which touched down in the Jezero crater on February 18, 2021, represents a quantum leap in our approach to the Red Planet. Its mission is not merely to explore or to analyze from a distance. It is to act as a cosmic archivist, a robotic curator meticulously collecting the most promising chapters of Martian history with the ultimate goal of sending them back to Earth for the most detailed analysis humanity can muster. This isn't just another rover mission. It is the first leg of an interplanetary relay race, a multi-stage campaign involving a lander, a fetch rover, a Mars ascent vehicle, and an orbiter, all working in concert to achieve what has long been the holy grail of planetary science, Mars sample return. The choice of its landing site, Jezero crater, was a masterstroke of scientific deduction. Orbital imagery had long told a compelling story of this location, the unmistakable topography of an ancient river delta, complete with channels that once carried water and sediments into a long-vanished lake. On Earth, river deltas are traps for organic material and biosignatures, the chemical signs of life. They are natural libraries preserving the story of an environment in their layered sediments. Perseverance is in effect drilling into the pages of this ancient book, using a sophisticated percussive drill at the end of its 7-foot-long robotic arm. The rover is coring into rocks, extracting pristine, pencil-sized samples of the most interesting and ancient materials it can find. Each sample is then hermetically sealed inside an ultra-clean titanium tube, one of over 40 it carries, creating a collection of geologic time capsules that are left in a carefully documented cache on the Martian surface, awaiting pickup by a future mission. The technological marvels accompanying Perseverance are not just support acts. They are revolutionary in their own right and have already expanded our consciousness of how we explore other worlds. The Ingenuity helicopter, a tiny 4-pound rotorcraft that hitched a ride on the rover's belly, was a high-risk, high-reward technology demonstration. It proved that powered, controlled flight is possible in the thin Martian atmosphere, which is just 1% the density of Earth's. Ingenuity's stunning success, far exceeding its planned 5 test flights, has opened a new dimension in planetary exploration. These aerial scouts can now act as pathfinders for future rovers, accessing treacherous terrain like cliff faces and craters that would be impossible for a wheeled vehicle to reach, providing a bird's-eye view that revolutionizes how we choose our scientific targets. Furthermore, Perseverance carries an experiment called MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment, which has successfully demonstrated the ability to extract breathable oxygen from the carbon dioxide that makes up 96% of the Martian atmosphere. This is not just a science experiment. It is a critical test of the technology that will one day allow astronauts to literally live off the land, manufacturing their own air and rocket propellant on Mars, turning a hostile environment into a more habitable one. This monumental endeavor forces us to adopt a new timescale for discovery, one that requires immense patience and long-term vision. Unlike the instant gratification of a picture sent back from a rover, the answers Perseverance seeks will not come for years, perhaps not until the early 2030s when the samples are finally delivered to state-of-the-art laboratories on Earth. These facilities will possess instruments far too massive and complex to ever fly to Mars electron microscopes that can reveal details 1,000 times smaller than a human hair, and equipment capable of dating the rocks with exquisite precision to determine the exact era when Jezero Crater was a living world. This patient, generational investment in knowledge reflects a mature understanding of science. Some questions are so profound that they are worth a decades-long, multi-billion-dollar international effort to answer. The ultimate promise of these samples is nothing less than a potential answer to one of the most fundamental questions we have ever asked. Did life ever arise anywhere beyond Earth? Finding even a single fossilized microbial cell in a Martian rock would be a discovery that would shatter our anthropocentric view of the universe and forever change our understanding of biology. It would suggest that the spark of life is not an incredibly rare and precious fluke, but a common, even inevitable, process in the right conditions. Conversely, if Perseverance's carefully selected samples, gathered from the most likely habitable environment on ancient Mars, come up entirely empty, devoid of any biosignatures whatsoever, that too would be a profound, if sobering, result. It would suggest that even with the right ingredients present, the emergence of life might be an exceptionally rare occurrence, forcing us to confront the haunting possibility that our pale blue dot might be even more unique and precious than we ever imagined. This patient gathering of rocks is therefore the most tangible step we have ever taken toward resolving our cosmic solitude, moving us from speculation toward evidence-based understanding of our place in the universe. After decades of planning, engineering setbacks, and breathless anticipation, the James Webb Space Telescope finally began its journey on Christmas Day, 2021. Perched atop an Ariane 5 rocket, it wasn't just another satellite being launched. It was a time machine, a promise to see further into the past than any instrument ever built. The tension didn't end at launch. For weeks, the world watched a high-stakes technological ballet unfold a million miles from Earth, as the telescope performed a complex series of hundreds of deployments, unfolding its golden mirror, stretching out a tennis court-sized sunshield, each step a single point of failure that could have doomed the entire $10 billion mission. Then, on July 11, 2022, the world held its breath once more as NASA prepared to release the first full-color images. What appeared on screens across the globe was not just data, it was art painted by the cosmos itself. The first deep-field image revealed a patch of sky no larger than a grain of sand held at arm's length, yet it was crammed with thousands of galaxies, each a swirling metropolis of stars, their light warped and magnified by the gravitational field of a foreground galaxy cluster. The clarity was breathtaking, the detail beyond anything Hubble had ever delivered. This wasn't an interpretation or an artist's impression. This was a direct photograph of the universe in its infancy. The psychological impact was immediate and profound. Webb's primary mission is to see the universe's first light, to witness the birth of those very first stars and galaxies that ignited after the Big Bang, ending the cosmic dark ages. Every time we look at a star, we are looking into the past, seeing it not as it is, but as it was when the light began its journey across the void. Webb takes this concept to its absolute extreme. By observing in the infrared part of the spectrum, its eyes are uniquely tuned to see the light from the most distant galaxies, whose light has been stretched into longer, redder wavelengths by the expansion of the universe over billions of years. When we look at Webb's deepest images, we are not just looking across space. We are gazing back across time, witnessing galactic construction sites as they were over 13 billion years ago, a mere whisper after the dawn of everything. This capability is already challenging our most fundamental models of cosmic evolution. Some of the galaxies in these early images appear too massive, too mature, too structured to exist so soon after the Big Bang. Their presence in such an ancient era forces astronomers to reconsider the timeline of how galaxies assemble, suggesting that the early universe might have worked much faster and much more efficiently than our theories ever predicted. Beyond the stunning deep fields, Webb's other first images revealed the full spectrum of its transformative power. The sight of the Carina Nebula, a stellar nursery of towering cosmic cliffs and glowing gaseous cavities, showed us star formation with a clarity that feels almost tangible, like we are flying through the cloud itself. The Southern Ring Nebula, a dying star expelling its outer layers into space, was revealed in intricate detail, a beautiful final act that seeds the universe with the heavy elements necessary for planets and life. The data hidden within these images is a treasure trove. By dissecting the light from exoplanet atmospheres as they pass in front of their host stars, Webb acts as a remote chemical sensor. It has already detected the unambiguous fingerprints of water vapor, methane, and even carbon dioxide in the skies of distant worlds. It found hints of potential biosignatures like dimethyl sulfide, a molecule on Earth produced only by life, in the atmosphere of a Hycean planet called K2-18b. While not proof of life, these detections are the first steps on a path that may one day lead to the definitive discovery of biology beyond our solar system. This new window onto the universe does more than just advance science. It fosters a deep, almost spiritual sense of connection. To look at a Webb image is to receive a postcard from a time before our sun, before our galaxy, even before most of the universe as we know it even existed. It is a direct visual link to our cosmic origins, a reminder that the atoms in our bodies were forged in the hearts of ancient stars and scattered across the galaxy by cataclysmic explosions like the ones Webb now observes. The telescope's stunning success is a testament to human perseverance, international collaboration, and our unquenchable thirst to understand where we come from. It prepares us not just for the discoveries we expect, but for the revelations we cannot yet imagine, the cosmic surprises that will inevitably force us to once again rewrite the story of everything. For all our gazing into the deep past with telescopes like the James Webb, and for all our planning of future outposts on other worlds, there remains a sobering, immediate truth. We exist in a dynamic and sometimes dangerous solar system. Our planet is constantly crisscrossed by the orbits of countless asteroids, remnants of the solar system's violent formation. For generations, our approach to this reality was purely passive. We watched, we tracked, we calculated probabilities, and we hoped that the really big ones would miss. That fundamental posture of cosmic vulnerability shifted on September 26, 2022, when a spacecraft the size of a vending machine deliberately slammed into a small asteroid called Dimorphos at over 14,000 miles per hour. This was the Double Asteroid Redirection Test, or DART, and it was humanity's first ever experiment in actively defending our planet. The target was chosen with brilliant precision. Dimorphos is not a threat to Earth. It's a moonlet orbiting a larger asteroid named Didymos. This binary system acted as the perfect natural laboratory. By carefully measuring Dimorphos's orbit around Didymos before and after the impact, scientists could quantify exactly how much the collision altered its path. The world watched the final moments live, seeing the asteroid grow from a distant pixel into a detailed, rocky landscape in the seconds before DART camera was obliterated on impact. The resulting data was unequivocal. The kinetic impactor technique worked, and it worked even better than modeled. DART suicide mission had shortened Dimorphos's orbit by a staggering 32 minutes, far exceeding the success benchmark of just 73 seconds. We had proven that with enough warning time, we could nudge a threatening asteroid off a collision course with Earth. This successful test represents a monumental shift in human consciousness, moving us from being passive inhabitants of a shooting gallery to active guardians of our world. It's the difference between merely installing a weather radar to track a hurricane and developing the technology to steer it away from the coast. This transforms our relationship with the cosmos from one of anxiety to one of agency. The knowledge that we are no longer completely helpless in the face of a potential extinction-level event is profoundly empowering. It reframes planetary defense from the plot of a Hollywood disaster movie into a serious, achievable branch of applied science and engineering, a global insurance policy written in mathematics and rocket fuel. The DART mission was also a stunning showcase of international collaboration and technological ingenuity. While led by NASA, it was a truly global effort. The Italian Space Agency provided a miniature CubeSat called LiSaCube that rode along with DART and flew past moments after the impact to capture the initial plume of ejected debris. Telescopes across the globe and in space, including the newly operational James Webb and Hubble, turned their gaze toward the Didymos system to observe the aftermath. And perhaps most significantly, the European Space Agency is now developing the Hera mission, which will journey to the asteroid later this decade to perform a detailed forensic analysis of the impact crater and precisely measure the mass of Dimorphos, turning the DART experiment's initial results into a comprehensive and refined understanding of how to deflect an asteroid. This proactive mindset extends beyond government agencies, fostering a culture of preparedness and innovation. The success of DART encourages further investment in advanced detection programs like the NEO Surveyor Space Telescope, which will be dedicated to finding and characterizing potentially hazardous objects years or even decades before they could pose a threat. It sparks new ideas and research into alternative deflection methods, such as using a spacecraft's gravity to gently tug an asteroid over time, or focusing solar energy to ablate its surface and create a tiny, continuous thrust. Most importantly, it reinforces a powerful, unifying truth that transcends borders. The threat of an asteroid impact is one of the few truly planetary challenges we face. It doesn't discriminate by nationality, wealth, or ideology. Protecting Earth from such a threat is therefore the ultimate shared human endeavor, a powerful reminder that our greatest achievements happen when we work together toward a common goal. This successful demonstration of our capability to safeguard our world ensures that as we continue to look outward with wonder, we also do so with wisdom and responsibility. For generations, the image of an astronaut was a highly specific one, a rigorously trained military test pilot or a career scientist, clad in a government-issued suit representing the pinnacle of a nation's technological might. The idea that an ordinary person, someone without a decade of specialized training, could ever venture beyond Earth's atmosphere was the stuff of fantasy. That fantasy evaporated on July 20, 2021, when billionaire Richard Branson, alongside several crewmates, soared to the edge of space aboard his company's V-Unity spacecraft. Just 9 days later, Amazon founder Jeff Bezos followed, accompanied by his brother and an 82-year-old aviation pioneer named Wally Funk, who had been denied her chance to become an astronaut 60 years prior because of her gender. In that single history-packed month, the era of commercial space tourism officially began, shattering the long-held monopoly of the astronaut corps and rewriting the rules of who gets to go. This shift is far more profound than a joyride for the ultra-wealthy. It represents a fundamental democratization of the cosmic perspective, a personalization of space that was previously unimaginable. For decades, the overview effect, that profound cognitive shift in awareness reported by astronauts who see Earth from space, was a second-hand experience. We heard about it in interviews and read about it in books, but it remained an abstract concept, a story told by a tiny, almost priestly class of individuals. Now that transformative experience is being opened up, one private flight at a time. The first tourists have returned with their own deeply personal accounts. They speak of the breathtaking thinness of the atmosphere, a fragile blue halo protecting all of known life. They describe the profound silence, the curvature of the Earth, and the total absence of the borders and conflicts that define so much of our terrestrial existence. This isn't just data being beamed back by a robot. It is lived, emotional testimony, and each new story makes that cosmic perspective feel more accessible, more human, and more universally relevant to everyone watching from the ground. This new accessibility is naturally seeding a broader cultural shift, fostering a society-wide culture of curiosity that extends far beyond the confines of professional aerospace. When children see a diverse array of people, not just career astronauts, but teachers, artists, and even their grandparents venturing into space, it fundamentally alters their perception of what is possible for their own lives. It makes space feel less like a distant government program and more like a domain of human experience, a place that might one day be within their own reach. This inspiration is the most valuable product of these early flights, arguably more so than the scientific data they collect. It generates a powerful ripple effect, encouraging a new generation to pursue studies in science, technology, engineering, and mathematics, not necessarily to become astronauts, but to become the innovators who will build the infrastructure, design the habitats, and solve the logistical puzzles of a future where space is a regular destination. Of course, this exciting new chapter is not without its complex and necessary ethical debates. The sight of billionaires funding their own orbital adventures while pressing problems remain unsolved on Earth has sparked intense discussion about priorities, wealth inequality, and the ethics of resource allocation. Critics rightly question the environmental cost of these launches, particularly the carbon footprint of rocket emissions in the upper atmosphere, prompting the industry to actively invest in developing more sustainable propellants and reusable launch systems. There are also crucial conversations about the long-term sustainability of space itself, centered on the growing issue of orbital debris and the urgent need for international agreements to prevent the commercialization of the cosmos from turning into a cosmic gold rush without rules, potentially polluting the very orbits we rely on for global communication and Earth observation. Yet, even amidst these vital debates, the cultural impact is undeniable. The live streams of these tourist flights, with their whoops of joy and tearful reunions, have a raw, relatable quality that differs from the polished professionalism of government missions. They make spaceflight feel less like a Cold War relic and more like a human adventure, something to be celebrated and shared. This normalization is a critical psychological step. It makes the concept of living and working in space feel less like science fiction and more like an inevitable part of our future, a natural extension of our curiosity and our desire to explore. By opening the door, even just a crack, to private citizens, these companies are not just selling tickets. They are building a market, driving down costs through competition, and funding the research that will lead to more reliable, frequent, and eventually more affordable access to orbit for many more people. This burgeoning industry, for all its growing pains, is laying the practical and philosophical groundwork for a future where looking down on our beautiful, fragile planet is not the end point of a rare and heroic career. but the beginning of a new, inclusive chapter in the human story. And so we arrive at a quest that predates rockets and telescopes, a question as old as humanity itself, whispered around campfires and debated in lecture halls for millennia. Are we alone? It's the most profound and humbling question we can ask of the universe, and for over 6 decades, we have been using our most advanced technology to try and listen for an answer. This is the ongoing search for extraterrestrial intelligence, an endeavor that represents not just a scientific mission, but the very embodiment of humanity's hope for cosmic companionship. It began in earnest in 1960 with Project Ozma, where astronomer Frank Drake pointed a radio telescope at 2 nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened patiently for any sign of an artificial signal amidst the natural cosmic static. That small project grew into SETI, the search for extraterrestrial intelligence, an institutionalized effort to scan the skies that continues to this day, constantly evolving with new technology and renewed hope. What's truly remarkable about this search is how it has expanded beyond the halls of major research institutions to become a global, collective effort. The public's fascination with this question is so powerful that it has spawned initiatives like SETI at Home, a program that allowed millions of ordinary people to donate their home computers' spare processing power to help analyze the mountains of radio data pouring in from telescopes. At its peak, it was one of the largest distributed computing projects in history, a quiet testament to how many of us are invested in this answer, how many of us want to be a small part of this grand generational investigation. This is science as a shared human project, a collaborative act of curiosity that transcends borders and unites people under a single, awe-inspiring question. It fosters a unique kind of international cooperation because the search knows no nationality. A signal from another star system would belong to all of Earth, not to any one country. The philosophical impact of this enduring search is perhaps its greatest gift to human consciousness. To actively look for other intelligences is to practice a radical form of humility. It forces us to confront the possibility, perhaps even the probability, that we are not the pinnacle of creation, that we might be just one voice in a grand galactic conversation that we can't yet hear. It encourages an open-mindedness that is essential not just for science, but for our growth as a species. The famous Drake equation, which attempts to estimate the number of communicative civilizations in our galaxy, is less about providing a definitive answer and more about framing the problem. It makes us consider the variables: how many stars have planets, how many of those planets are habitable, how often does life arise, and if it does, how often does it become intelligent, and how long does such a civilization last? Each term in the equation is a mirror, reflecting our own uncertainties back at us and prompting deep introspection about our own future. This search beautifully bridges the cold, hard logic of science with the deep, human yearnings of philosophy. On one hand, it involves exquisitely sensitive radio telescopes, complex algorithms to filter out terrestrial interference, and the meticulous analysis of electromagnetic spectra. On the other hand, it is driven by our most fundamental curiosities about meaning and existence. What is our purpose? Is life a miraculous fluke or a cosmic imperative? The search for an answer, even in the continued silence, transforms how we view our place in the cosmos. It promotes a sense of shared purpose, a feeling that we are all in this together on our small, fragile planet, waiting for a sign that we are not the universe's only children. The very act of listening is an act of hope, a statement that we believe there is something worth hearing. And while that definitive, universe-altering signal has not yet been found, the effort itself is its own reward. It keeps the question alive, ensuring that we never become so arrogant, so earth-bound in our thinking that we stop wondering what else might be out there. This ongoing journey reminds us that true exploration is not just about the answers we eventually find, but about the profound beauty and importance of the questions we dare to ask. Together, these 24 moments weave a grand tapestry of discovery, illustrating a profound and repeated transformation in how we see ourselves and our place in the cosmos. From that first beeping sphere that pierced the silence of space to the stunning deep-field images that peer back to the dawn of time, each breakthrough has done far more than just advance our technology. They have acted as mirrors, reflecting our own image back at us from new and startling vantage points, forcing us to shed old assumptions and embrace a wider, more unified perspective. We began this journey looking up at a distant, unreachable sky, and we have ended it looking back at a fragile, borderless oasis we all share. This shift from earthbound concerns to cosmic contemplations is perhaps the most significant legacy of the space age, a permanent expansion of human consciousness that has redefined our very sense of purpose. These milestones remind us that the greatest value of exploration lies not solely in the new worlds we find, but in the deeper understanding of our own. Every time we reached for another horizon, whether it was the lunar surface or the atmosphere of a distant moon, we were ultimately learning something vital about humanity, our capacity for courage, our genius for innovation, our resilience in the face of crisis, and our profound ability to work together toward a common goal that transcends any earthly division. The overview effect, experienced by astronauts and channeled to the rest of us through breathtaking imagery, is more than a beautiful perspective. It is a vital cognitive tool for navigating the challenges of the 21st century. It teaches us humility, stewardship, and the undeniable truth that we are all crew members on the same spaceship, hurtling through the void together. As we now stand on the brink of becoming an interplanetary civilization, with ambitions stretching from a sustainable presence on the Moon to the first human footprints on Mars, let these historical moments serve as both inspiration and instruction. They are a foundation of courage and curiosity upon which we must build. Let them inspire you to look up at the night sky with a renewed sense of wonder, to support the scientific and educational endeavors that make such leaps possible, and to actively participate in the great conversations about our future in space. But let them also remind you to cherish and protect our beautiful, fragile planetary home, the only one we have for now, the pale blue dot that will always be our origin point. This story is far from over. In fact, it feels as though the most thrilling chapters are yet to be written. The next great discovery, perhaps evidence of life on another world, or contact with an intelligence beyond our own, awaits us, and it promises to once again revolutionize everything we think we know. So we pass the torch of curiosity to you. Share the moment that most expanded your own mind in the comments below. Join this community of wonder and subscribe for more journeys into the cosmos. The greatest adventure lies ahead, and it belongs to all of us. Keep looking up, keep questioning, keep exploring. Yet as monumental as these past moments have been, they are merely the prelude to an even more astonishing future, a horizon of possibilities that promises to reshape human consciousness in ways we are only beginning to fathom. The next great leaps will not merely be about going farther or seeing more. They will fundamentally alter our understanding of life itself, our place in the cosmos, and the very fabric of reality. Imagine the day, perhaps within our lifetimes, when the first human footsteps are pressed into the rusty soil of Mars. This will be more than a historical achievement. It will be a profound psychological event for our entire species. To see a live broadcast of a person standing on another planet, looking up at a pale blue sun in a pinkish-orange sky, will forever dismantle the notion that humanity is bound to a single world. It will make interplanetary existence a tangible reality, forcing us to confront exhilarating and daunting questions about what it means to be a multi-planetary civilization. Will we take our old conflicts with us, or will the sheer challenge of survival on a hostile world foster a new era of unprecedented cooperation? The very act of trying to keep humans alive on Mars will drive breathtaking innovations in closed-loop life support, sustainable agriculture, and medicine, technologies that will inevitably benefit life on Earth and cement our identity as a spacefaring species. But our future reach extends far beyond Mars. Envision sophisticated probes diving into the subsurface oceans of moons like Europa and Enceladus, not just to sample water, but to actively hunt for living organisms. The confirmed discovery of even simple extraterrestrial life, a second genesis independent of our own, would represent the single most transformative moment in human history. It would prove that the recipe for life is not a unique fluke confined to our planet, but a common, perhaps inevitable, process woven into the fabric of the universe. This realization would force a monumental shift in our philosophical and theological frameworks, challenging centuries of anthropocentric belief and answering the ancient question of whether we are alone with a resounding and humbling no. The field of biology would explode overnight, expanding from a single day to point to a universal science, and our understanding of life's potential, its resilience and variety, would be forever rewritten. This search for life is now being supercharged by a new generation of tools. Giant 30-meter class telescopes on the ground and advanced space observatories will soon be able to analyze the atmospheres of Earth like exoplanets, searching for biosignatures, chemical imbalances like the presence of oxygen and methane that could be the telltale signs of a living biosphere. We are on the verge of moving from wondering about life on other worlds to actively taking its census. Concurrently, the economic and practical foundations of our future in space are being laid through ventures that once belonged solely to science fiction. The concept of asteroid mining is rapidly moving from theoretical models to serious business plans. These celestial rocks are not just barren rubble. They are floating mountains of precious metals like platinum and gold, as well as vital resources like water ice. This water is the oil of spaceflight. It can be split into hydrogen and oxygen for rocket fuel, used for life support, or even shielded against radiation. The ability to harvest fuel and building materials from asteroids instead of launching them from Earth's deep gravity would completely revolutionize space travel, making it infinitely cheaper and more sustainable. It would enable the construction of large, permanent structures in orbit, space hotels, manufacturing facilities, and even generation ships designed for interstellar travel. This birth of a space-based economy will force us to develop entirely new legal and ethical frameworks. Who owns an asteroid? How do we manage off-world resources to avoid the exploitative patterns of our past? Navigating these questions will be a critical test of our species' maturity, demanding a balance between ambitious exploration and responsible stewardship of the solar system we are beginning to inhabit. Underpinning all of this will be a revolution in how we communicate across these vast new frontiers. The frustrating delay of minutes for a signal to travel between Earth and Mars is a major hurdle for exploration and a palpable feeling of isolation for crews. The future lies in moving from radio waves to quantum communications and laser-based optical systems, which promise not only instantaneous data rates thousands of times faster, but also potentially unhackable quantum encryption. This will create a true interplanetary internet, a nervous system connecting human outposts across the solar system, allowing for real-time control of robots on distant moons and virtual presence on alien worlds. It will shrink the psychological distance of space, making the cosmos feel more connected and accessible. This incredible future, brimming with both promise and profound responsibility, circles back to a crucial, grounding truth. Our expansion into the solar system must be guided by a dual commitment: to explore the heavens with boldness and ingenuity, while also serving as dedicated guardians of our first and most precious home, Earth. The technologies we develop to live sustainably on Mars, to clean up orbital debris, and to harness solar energy in space can and must be applied to solving our environmental challenges here. The overview effect, once a rare experience for a select few, must become a guiding principle for all of humanity, a constant reminder of the breathtaking beauty and fragility of our pale blue dot. This journey ahead is not about escaping Earth, but about enriching our existence by broadening our horizons, ensuring that as we reach for the stars, we remain forever committed to nurturing the world